Okay, welcome to the Deep Dive. This is the show where we take your stack of sources, dive right in, and pull out the most important knowledge and insights.
Yeah, it's all about getting you informed quickly, cutting through the noise to find those surprising facts.
Exactly. And today, we're looking at something pretty remarkable based on the material you shared with us. We're doing a deep dive into an engine that's, well, it's earned some serious respect.
And a couple of great nicknames, too. The Ford 2.7-liter EcoBoost V6.
That's right. Our mission today really is to understand the engineering behind this specific engine. How did Ford manage to pack such impressive performance and efficiency into a package that's, frankly, pretty compact?
It's often called the Nano, sometimes the Pocket Hercules. So what is it about this engine? What makes it punch so far above its weight class? Let's unpack this.
So the story of the 2.7-liter,
Okay.
it really builds on Ford's success with its bigger sibling, right? The 3.5-liter EcoBoost V6.
Okay.
They'd proven the concept there, so the decision was made to, scale that tech down. And that scaled-down version arrived when?
2015.
2015, yeah. First showed up in the Ford F-150 pickup truck for that model year.
Right. And the initial numbers were pretty eye-opening.
Oh, yeah. 325 horsepower and 375 pound-feet of torque right out of the gate.
And that's the thing that really jumps out. In the sources, those numbers were right there with, sometimes even better than, a lot of the naturally aspirated V8s available then.
Absolutely. But the big advantage, the real kicker, was the fuel economy. The 2.7 did it while being significantly more efficient.
So you got that V8-like power, that grunt, especially the torque you need for truck stuff, but in a smaller, lighter engine that didn't guzzle gas nearly as much.
Exactly. That combination performance, efficiency, compact size, that's what defined its appeal early on, and that's where those nicknames came from.
Makes sense. Nannied for the small size, displacement. And Pocket Hercules really nails that idea. Something small but incredibly strong, especially that first generation. Okay, so how did they actually do it? This is where the engineering gets really, really interesting. We're talking the first generation here, 2015 to 2017.
All right, what's the first big piece? Where do we start?
You got to start with the twin turbochargers. I mean, that's core to the EcoBoost concept.
Okay.
Instead of just relying on atmospheric pressure, they use the engine's own exhaust gases to spin these turbines. Those turbines then force more air into the engine. It's fundamental to getting big power from a small displacement.
And having two of them, the twin part, that matters.
Oh, definitely. Two smaller turbos spool up much faster than one big one, so you get significantly less turbo lag.
So quicker response when you hit the gas.
Much quicker. More immediate throttle response, that really contributes to that Pocket Hercules feel. More air means you can burn more fuel efficiently and make serious power.
Got it. So more air coming in, how's the fuel getting there?
That's the next piece. Direct fuel injection. The fuel is sprayed directly into the combustion chamber, not into the intake port like older systems.
And the benefit there?
It allows for really precise fuel metering. You get a better air-fuel mixture right in the cylinder for a cleaner, more efficient burn. The sources also point out it helps prevent detonation engine knock, which is a big risk when you're running high boost from turbos. Gives it that solid, almost diesel-like performance feel some people mention.
Now, something else that seems really unique highlighted in the sources is the block material. Compacted graphite iron, CGI.
Yes, that was a big deal. Ford's first use of CGI in a gasoline engine?
They'd use it before, though.
In diesels, yeah. Like the 6.7-liter Power Stroke V8 and apparently a 2.7-liter light-duty diesel, too. CGI is incredibly strong, very durable, and it handles heat really well.
I saw some numbers comparing it to traditional gray iron. Ed Wachenko, Ford's V-engine design leader, he said something like 75% higher tensile strength.
Yeah, and 45% stiffer, roughly double the fatigue strength. I mean, the properties are just way beyond regular cast iron.
So what does that let them do, using the stronger material?
Well, because it's so strong, Ford could design the block with thinner walls and narrower main bearing saddles. This directly helps make the engine physically smaller and lighter than a traditional block that could handle the same power.
So it's not just strong, it enables the compact size.
Exactly. It's fundamental to the whole Nano concept. And the block design itself is kind of unusual, too. It's a two-piece setup.
Two pieces? How does that work?
Okay, so the upper part, where the cylinders live, that's the strong CGI. But the lower section is actually a die-cast aluminum ladder frame.
Aluminum ladder frame.
Yeah, it bolts onto these special flanges on the bottom of the CGI block, and it's what supports the main bearing caps. Creates a really rigid structure for the crankshaft.
And those main bearing caps, I read about fracture split caps, also CGI. Sounds complicated.
It's pretty clever, actually. They make the cap, laser etch a line on it, and then literally fracture it, break it right along that line, usually at an angle.
They break it on purpose.
Yep. Because then, when you bolt the two pieces back together around the crankshaft journal, those rough, fractured surfaces made up perfectly. It's a unique fit for each cap. Washchenko apparently even said the fit is so precise, the engine could theoretically run without the cap bolts, at least initially.
Wow. Okay, so that's super tight fit.
Yeah.
What's the advantage?
It creates an incredibly stable base for the crankshaft, reduces tiny movements, less friction, better efficiency, and just adds to the overall durability, especially under the high loads from the turbos. It's another one of those details showing how much thought went into strength and efficiency.
The connecting rods, too, had some interesting features mentioned.
They did. The small end, up by the piston pin, it's linerless, no bushing. Instead, it has this silicone-coated bore that's actually slightly convex, believe it or not.
Convex why?
It allows the piston pin to flex just a tiny bit under load. And getting rid of the bushing there let them shave off 3 millimeters from the engine's overall height, the deck height, down to 218.3 millimeters, or about 8.6 inches. Again, a small detail, but it adds up to making the engine more compact.
And the other end connecting to the crank.
Those are cracked connecting rods, similar idea to the main caps for a precise fit, and they use an offset I-beam design. Strong enough for the peak power, but designed to be lighter for better engine responsiveness. And critically, the sources emphasize, Ford used a forged crankshaft and forged connecting rods. Robust stuff, essential for an engine they wanted to perform like a V8.
Heat seems like it would be a major challenge, especially with turbos packed in there. I saw something about integrated exhaust manifolds.
Right. Instead of bolting separate manifolds on, they cast them right into the cylinder heads.
Ah, clever. Save space.
Save space makes the whole package more compact, and importantly, it helps transfer heat out of the head and into the exhaust more quickly. This helps the catalytic converters warm up faster after you start the engine, which is good for emissions.
And the cooling system itself is different. Reverse flow.
Yeah, it's a reverse flow setup. Once the engine warms up and the thermostat opens, the coolant goes through the cylinder heads and those hot integrated exhaust manifolds first. Then it flows down through the block. It's a way to manage combustion chamber temps more effectively, keep things cool where it matters most.
Okay, so that covers a lot of the core mechanicals. But there were smart technologies layered on top too, right?
Absolutely. Auto start-stop was standard, at least in the F-150. Saves fuel by shutting the engine off when you stop, but they tuned it specifically for trucks it wouldn't shut off if you were towing or in four-wheel drive.
Smart. Makes sense for truck use.
And there was all new engine control logic. Basically, the computer could adjust things like spark timing, fuel injection, boost pressure, constantly on the fly, based on how you were driving, the temperature, the load, always aiming for the best mix of efficiency and power.
Things like a variable displacement oil pump.
Yeah.
That helps efficiency.
Yeah, it reduces internal friction. The pump only supplies the oil pressure that's actually needed at that moment instead of running full blast all the time. Saves a little bit of energy, improves fuel economy. And then there's TIE VCT.
TIE VCT. What's that stand for again?
And what's it? Twin independent variable cam timing. Basically, the engine can change when the intake and exhaust valves open and close independently of each other.
Okay.
This lets the engine optimize airflow for better torque across the RPM range, especially low-end torque, while also helping reduce emissions. It's pretty standard tech now, but it was part of the package here.
They also used a composite intake manifold. Lighter, I assume?
Lighter, yeah. And durable.
Yeah.
And crucially, cooling jets. Little nozzles that spray engine oil onto the underside of the pistons.
Why do that?
Keeps the pistons cooler. Really important in a turbocharged engine where those pistons see a lot of heat under boost.
Yeah.
Helps them last longer, prevents damage. Oh, and for easier maintenance, the oil filter is a cartridge style right up top. Easy to get to.
I saw a quote from Raj Nair, who was a big deal at Ford then. He described the 2.700 EcoBoost as combining a host of advanced technologies to create one of the most technically advanced and efficient engines ever designed.
And when you list it all out, like the CGI block, twin turbos, direct injection, those fracture split caps, the advanced cooling, all the variable systems, you see, it wasn't just one trick. It was integrating a whole suite of cutting-edge ideas together. That really underscores the engineering feat aspect. Okay, so all this tech sounds great on paper, right? But how do you prove it's actually tough? Especially when you're putting it in an F-150 and calling it truck ready.
Right, which brings us to Ford's testing. The sources mentioned it was Pretty brutal. What's the big example everyone talks about?
The Baja 1000 test. It's almost legendary now. Ford took an F-150, kind of disguised, but crucially, it had a completely stock 2.70 EcoBoost engine.
Stock. Like off the assembly line stock.
Stock. No extra oil coolers, no engine mods you normally do for desert racing. And they entered it in the Baja 1000. That's an 883-mile off-road race through Mexico. Insanely tough on vehicles.
They touted to do.
It finished the race, the whole thing. And the sources are clear. The only part they changed on the engine itself during the entire event was the stock air filter.
That's incredible.
Yeah.
Finishing Baja with a stock engine.
It's a massive statement about the fundamental durability they engineered into it. Real-world proof, not just lab numbers.
Speaking of labs, what else did they put it through?
Oh, tons of stuff. Over 1,000 extreme temperature cycles. They run it from -25 Fahrenheit all the way up to 235 Fahrenheit over and over. Like driving from Death Valley to the Arctic Circle 350 times, the sources say.
Wow. Just cycling between extremes.
And structural fatigue tests. Running the engine at full load, peak torque, peak power for over 17 days straight.
17 days at full tilt.
Yeah. Plus, over 900 hours just testing the start-stop system, simulating like 240,000 starts and stops, and over 800 hours of towing tests, unloaded driving tests across the whole power range, using different fuel mixes, even intentionally bad oil, just to push it to its absolute limit.
Okay, yeah. That level of testing definitely backs up the idea that they didn't just aim for power and efficiency, they really focused on making it tough and reliable too.
So they build this really innovative, really tough first-gen engine. What comes next? What did they learn? How did they improve it?
That leads to the second generation. Yeah. Introduced around 2018, it incorporated updates similar to what they did with the bigger 3.5-liter EcoBoost.
Exactly. The goal was to enhance reliability, capability, and efficiency even further.
And what were the key changes there?
Probably the biggest single update was the fuel system. Gen 1 was direct injection only, right? Fuel straight into the cylinder.
Right.
Gen 2 adds what they call twin port and direct fuel injection.
Twin port. So 2 injectors per cylinder now.
That's it. You still have the direct injector in the cylinder, but now there's also a second injector in the intake port, upstream of the valve.
Okay, why add the second injector?
They work together, gives even finer control over fueling, which helps with both efficiency and power. But maybe the biggest long-term benefit, especially for reliability, that port injector washes fuel over the back of the intake valves.
And that helps with
carbon buildup. Direct injection-only engines can sometimes get carbon deposits on the intake valves over time because there's no fuel washing over them. Adding the port injection helps keep those valves clean. It was a really smart way to address a potential long-term issue.
That makes a lot of sense. What else did they tweak for Gen 2?
The twin turbos got revised, and importantly, they now use an electrically controlled wastegate instead of vacuum actuated.
Better boost control.
More precise boost control, yeah. Leads to better throttle response again, and helps optimize efficiency.
Any other significant changes?
Let's see. They added a new high-pressure EGR system, exhaust gas recirculation. That helps with emissions. There's a dual-chain camshaft drive system now with lighter camshafts. And they kept or refined that electronic variable displacement oil pump to keep friction down.
I saw a note about the oil pump drive. A wet belt.
Yeah, it uses a special belt made of Kevlar that actually runs inside the engine, lubricated by the engine oil. Now, some earlier, smaller EcoBoost engines had some reported issues with wet belt designs.
Okay.
But the sources specifically mentioned that for the 2.7-liter version, widespread problems haven't really surfaced. Seems like they got this implementation right. It's likely pretty robust.
So how did all these Gen 2 changes affect the actual performance numbers, say, in the F-150?
Well, peak horsepower stayed the same, 325 HP. But it now hit that peak a bit earlier in the rev range, 5,000 RPM instead of 5,750.
Okay. And torque?
Torque got a nice bump, up 25 pound-feet to 400 pound-feet total.
That's a healthy increase. Did that peak torque come earlier too?
Yeah, generally. Depending on the specific model year, like 2018, 2020 versus 2021 plus Saro, that peak torque comes in around 2,750 or 3,000 RPM. The Gen 1 peak was at 3,000 RPM. So more twisting force, available a bit lower down, which is great for drivability.
And these Gen 2 engines often got paired with the newer 10-speed automatic, right?
Oh, yes, the 10R80 or sometimes the 10R60. That transmission helps keep the engine right in the sweet spot of its power band more often.
And there was one more update noted for 2021 onwards.
Sources mentioned they added beefier pistons, specifically with oil cooling galleries built into them. Just another small refinement aimed at long-term durability, especially for folks who work these engines hard.
Okay, so Gen 2 really seems like they took that strong foundation, addressed potential weaknesses like the carbon buildup, refined the systems, and squeezed out a bit more usable torque.
Yeah, and if you kind of pull out the key specs from the sources, lay them side by side, you really see that evolution clearly.
Both generations built in Lima, Ohio. Still a V6 DOHC, still 2.7 liters or 164 cubic inches. And that interesting square bore and stroke, 3.27 inches by 3.27 inches.
Right. The core structure is the same. That CGI upper block, aluminum lower ladder frame, aluminum heads, roller finger follower valvetrain, coil on plug ignition, all that carried
Well,
over.
compression ratio nudged up slightly, didn't it? 10.0 to 1 for Gen 1, up to 10.3 to 1 for Gen 2 Plus.
Yep. Firing order stayed the same too, 142536.
But the big difference is really that fuel system. Direct injection only in Gen 1.
And then the port plus direct injection combo for Gen 2. That's the major mechanical differentiator. Both are twin turbo, both intercooled, but Gen 2 added those electronic wastegates for finer control.
And the performance numbers reflect those changes. Gen 1, 325 horse at 5,750 RPM, 375 torque at 3,000. Gen 2, still 325 horse, but at 5,000 RPM now, and torque up to 400 pound-feet, hitting peak around 2,750 to 3,000 RPM.
And important to note, for standard output versions, they're designed to run fine on regular unleaded fuel. Oil capacity is 6 quarts for both. You know, there's one other really fascinating point that comes up in the source material. The tuning potential.
Oh, really? People are modifying these things. How far can they push them?
Apparently, quite far. The sources note that the basic engine design, especially that super strong CGI block, is so robust that tuners with things like upgraded turbos, beefed up fuel systems, and running high ethanol E85 fuel, they're seeing power figures up in the 600 to 650 horsepower range.
600 horsepower from a 2.7-liter V6.
Yeah, it really shows just how much headroom, how much strength Ford engineered into the core components right from the factory.
Okay, so let's kind of wrap this all up. We've gone through a ton of technical detail. What does it all mean for you, the listener, if you're interested in this engine, maybe own one or are thinking about one?
I think it tells a compelling story. It's the story of an engine that was very purposefully designed. Ford used advanced materials, like that CGI, and innovative engineering choices to tackle a specific problem.
Which was?
How do you get V8-level performance and capability, especially that low-down torque people want in trucks, but package it in a smaller, lighter, much more fuel-efficient V6?
And all those features we talked about, the CGI block, giving strength without weight, the quick spooling twin turbos, the precise fuel injection that got even better with Gen 2's dual system, the clever cooling, the variable timing.
Exactly. They weren't just features thrown in. They were all calculated engineering decisions working together. That's what allows this relatively small engine to perform so far beyond what its size might suggest. It really does earn that Pocket Hercules nickname.
And knowing about the testing, like that Baja 1000 finish with a stock engine, that adds a layer of confidence, doesn't it? Despite all the complex tech, it was built to be durable, built to handle tough work.
For sure. It's really a fantastic case study in modern powertrain engineering, balancing power, efficiency, durability. It's quite an achievement.
So we've taken a really thorough deep dive into the Ford 2.7-liter EcoBoost V6. We've explored its innovative design, looked at the tough testing it endured, and tracked its evolution from Gen 1 to Gen 2, all based on the sources you shared.
Yeah, we've seen how those specific choices, the CGI block, the fracture split caps, the twin turbos, the dual injection system later on, how they all fit together to create an engine that's, well, it's a genuine engineering marvel in many ways.
So here's a final thought to leave you with. As engineers keep packing more and more complex technology into smaller engines, trying to hit those tough targets for power, fuel economy, emissions, how does understanding the specific how and why behind the features in an engine like this, 2.7-liter EcoBoost, how does that change the way you think about the engines that power the vehicles you rely on every single day?